Picture this. It is 1947, and Richard Feynman, already celebrated as one of the brightest minds in physics, is staring at a piece of paper covered in equations. And those equations are telling him something impossible. They are telling him that the charge of an electron is infinite, that the energy of empty space is infinite, that everything, everywhere, when you try to calculate it precisely, explodes into mathematical nonsense. Feynman's beautiful theory of quantum electrodynamics, the crown jewel of 20th century physics, is broken. Completely, devastatingly broken. And here is the remarkable part. Magnesi, on Dirchenstechsti, what mote, di I. Feynman did not run from this disaster. He did not hide it, or pretend the problem would go away. Instead, he did something that separated him from merely brilliant scientists and made him a legend. He stared directly into the face of that impossibility and asked the most dangerous question in physics. What if we are thinking about this completely wrong? Now, before we can understand the crisis that nearly destroyed quantum physics, we need to understand what Feynman was trying to calculate in the first place. And this requires us to confront one of the strangest ideas in all of science. Empty space is not empty. You are probably sitting somewhere right now, looking at the air around you, thinking it is mostly nothing. Maybe some oxygen molecules floating around, some nitrogen. But between those molecules, pure emptiness. Nothingness. Wrong. Don't see. Spectacularly, beautifully wrong. The quantum vacuum, which is what physicists call empty space, is seething. It is alive with activity. At every point in space, at every instant of time, particles are flickering into existence and then vanishing again. Electron-positron pairs materialize out of nothing, exist for an impossibly brief moment, and then annihilate each other. Quarks and antiquarks bubble up and disappear. Photons appear and are absorbed before they can travel anywhere. These are called virtual particles. And before you ask, yes, they are real. We can measure their effects. We can see their fingerprints on experiments. The vacuum is not a stage where physics happens. The vacuum is a participant. Imagine you are trying to measure the charge of an electron. Simple enough, right? Electrons have a charge. It is one of the most fundamental properties in nature. We call it the elementary charge, and every introductory physics textbook will tell you its value. But here's the problem Feynman ran into. When you try to calculate that charge from first principles, using the beautiful mathematics of quantum field theory, you do not get a number. You get infinity. Why? Because of vacuum polarization. Think of it this way. Imagine you drop a single charged particle into the quantum vacuum. That particle creates an electric field around itself, as all charged particles do. But the vacuum is not passive. The vacuum responds. Those virtual electron-positron pairs that are constantly flickering in and out of existence, they feel that electric field. And they orient themselves. The virtual positrons, being positively charged, are attracted slightly toward your electron. The virtual electrons are pushed slightly away. The vacuum becomes polarized, like iron filings aligning around a magnet. Now here is where things get strange. This polarization partially shields the charge of your original electron. An observer far away sees a slightly weaker charge than the bare electron actually has. The vacuum is screening the electron's true charge. But wait. There is more. Those virtual particles that are screening your electron, they have electric fields too. And those electric fields polarize even more virtual particles, which have their own electric fields, which polarize still more virtual particles. And this cascade continues, layer upon layer, all the way down to infinitely small distances. When Feynman tried to calculate this effect, summing up all these contributions, the mathematics exploded. The corrections became infinite. Not large. Infinite. The theory was telling him that the charge of the electron properly calculated should be infinitely large. This was the vacuum polarization crisis. And it was not just Feynman's problem. Every physicist working on quantum electrodynamics in the 1940s was hitting the same wall. But here is where it gets interesting. Around the same time, Feynman was wrestling with these infinities on paper. An experimentalist named Willis Lamb was doing something remarkable in his laboratory. He was measuring the energy levels of hydrogen atoms with unprecedented precision. And he found something that should not have been there: the Lamb shift. Two energy levels in hydrogen that, according to classical quantum mechanics, should have been identical, were actually slightly different. The difference was tiny, about 1 part in a million. But it was real. It was measurable, and the existing theory could not explain it. Now, you might think that experimentalists finding something theorists cannot explain is a disaster, but Feynman saw it differently. This was a gift. This was the universe giving him a clue, because the Lamb shift, it turned out, was caused by vacuum polarization. Those virtual particles flickering around the electron in a hydrogen atom were shifting its energy levels by exactly the amount Lamb measured. The effect that was making Feynman's calculations blow up to infinity was the same effect creating a real, measurable phenomenon in the laboratory. The infinities were not nonsense. They were trying to tell him something. Let me give you an analogy that might help here. Imagine you are trying to measure the height of a mountain. Well, you start at what you think is sea level, but you discover that sea level is actually sitting on top of an ocean, which is sitting on top of a continental plate, which is sitting on top of the mantle, which goes all the way down to the center of the earth. If you try to measure the mountain's height from the true bottom, you get an absurdly large number that includes the entire radius of the planet. But that is not useful. No one cares about the mountain's height measured from the Earth's core. What matters is the height from sea level, the height you can actually observe and use. Feynman realized that quantum field theory was making the same mistake. It was trying to calculate the bare charge of the electron, the charge measured from infinitely close up, through all those layers of virtual particle polarization. And that bare charge might well be infinite, but we never see the bare charge. We cannot get infinitely close to an electron. What we observe, what we measure in experiments, is the screened charge, the effective charge seen through all those layers of vacuum polarization. What if, Feynman asked, we simply agree to express everything in terms of the measured charge, the one we actually observe, instead of the unknowable bare charge? This idea became known as renormalization, and it transformed physics. The concept is subtle, so let me try another way of explaining it. Suppose you are trying to calculate the interest on a bank account, but every time you do the math, you get infinity because of some weird compounding effect that goes back to before the universe began. A practical banker would say, forget about where the money came from originally. Just tell me what is in the account today, and calculate forward from there. That is renormalization. You absorb the infinities into the definitions of your measured quantities, the quantities you can actually observe, and then everything else becomes finite and calculable. It sounds like a trick. It sounds like cheating. Feynman himself called it a dippy process for most of his career. He was never fully comfortable with it. He felt they were sweeping infinities under the rug rather than truly understanding them. But here is the thing. It works. Spectacularly. Using renormalization, Feynman calculated the Lamb shift. His prediction matched Lamb's measurement to 6 decimal places. Think about that. A theoretical calculation predicting an experimental result to better than 1 part in a million. Then came the anomalous magnetic moment of the electron. An electron is like a tiny spinning magnet. Quantum mechanics predicts the strength of this magnetism to be exactly 2 in certain units. But the actual measured value is slightly different. It is 2.002319304, give or take. Feynman's renormalized quantum electrodynamics predicted that number. The theory agreed with experiment to more than 10 decimal places. This remains the most precisely verified prediction in all of science, better than any other theory has ever achieved in any field of human knowledge. The theory that gave infinities, the theory that seemed hopelessly broken, had become the most accurate theory humans have ever devised. But here is where we need to go deeper, because the story of vacuum polarization is not just about fixing a mathematical problem. It reveals something profound about the nature of reality. Remember those virtual particles constantly flickering in the vacuum? They do not just screen electric charges. They do something even stranger. They make the strength of forces change depending on distance. When you measure the electric charge of an electron from far away, you see it through many layers of vacuum polarization, heavily screened. The charge appears relatively weak, but if you could somehow probe the electron from very close up, at very high energies, you would punch through some of that screening. You would see a stronger charge. This is called the running of coupling constants, and it is not just theoretical speculation. We have measured it. At particle accelerators like the Large Hadron Collider, when protons collide at enormous energies, we can probe distances far smaller than the size of an atom, and we see the electromagnetic force getting stronger, exactly as vacuum polarization predicts. The vacuum is not just empty space with some quantum fuzz. The vacuum determines the very strength of the forces of nature. What we call the charge of the electron is not a fixed property of the electron at all. It is a relationship between the electron and the vacuum that surrounds it. Now, you might be thinking, this is all very interesting for particle physics, but what does it have to do with me? Here is what it has to do with you. You exist because of vacuum polarization, the nuclear force that holds protons and neutrons together in the nuclei of your atoms. It behaves in exactly the opposite way from electromagnetism. The strong nuclear force has a property called asymptotic freedom, which means it gets weaker at short distances and stronger at long distances. This is vacuum polarization running in reverse, because the virtual particles involved are different types, gluons, instead of electron-positron pair. If vacuum polarization worked the same way for the strong force as it does for electromagnetism, protons and neutrons would fly apart. Atomic nuclei would be impossible. Chemistry would be impossible. You would be impossible. The bizarre quantum properties of empty space, the same properties that gave Feynman infinite headaches in 1947, are why you are here to read about them. Let us pause for a moment and consider what Feynman actually accomplished. He started with a theory that was giving nonsensical answers. Infinities everywhere. Mathematics breaking down. By any reasonable standard, the theory was wrong. But instead of abandoning it, he asked a deeper question. What are we actually measuring? What can we actually observe? He realized that the infinities arose from asking questions about quantities we could never access, like the bare charge of an electron at zero distance. When he reformulated everything in terms of observable quantities, the theory not only worked, but became the most precise theory in the history of science. There is a lesson here that goes far beyond physics. When you hit an impossible answer, when your calculations or your thinking leads you to nonsense, the problem might not be with your reasoning. The problem might be with your assumptions. The problem might be that you are asking the wrong question. Feynman did not solve the vacuum polarization crisis by being smarter than everyone else at doing the same calculations. He solved it by realizing that everyone, including himself, was calculating the wrong thing. And there is one more twist to this story that we should not ignore. Feynman never claimed that renormalization was the final answer. He called it a shell game. He worried that future physicists would discover that the infinities they were sweeping away contained crucial information about deeper physics. We still do not know if he was right to worry. Quantum electrodynamics works beautifully. Its predictions match experiments to astonishing precision. But when physicists try to apply the same techniques to gravity, everything falls apart. The infinities cannot be absorbed away cleanly. Gravity refuses to be renormalized. This suggests that either our understanding of gravity is incomplete, or our understanding of quantum field theory is incomplete, or both. The vacuum polarization crisis that Feynman thought he had resolved may have only been the first chapter of a longer story. Some theorists have proposed wild ideas. Maybe space itself is discrete at the smallest scales, and that is why the infinities appear when we pretend it is continuous. Maybe gravity requires us to think about space-time in an entirely different way, as suggested by string theory or loop quantum gravity. Maybe the vacuum has structure we have not yet imagined. There are even speculative ideas about whether the energy of vacuum polarization All those virtual particles, constantly flickering in and out of existence, could be harnessed somehow. Could we extract energy from the vacuum? Could we create propulsion from the quantum foam? The answer for now is almost certainly no. The conservation laws of physics are strict, and every attempt to cheat them has been frustrated. The forces created by vacuum fluctuations, like the Casimir effect where two metal plates attract each other due to suppressed vacuum modes between them, are real but tiny, and they cannot give us free energy or thrust without paying the full price in input work. But the fact that we are even asking these questions shows how far we have come from thinking of empty space as truly empty. Richard Feynman died in 1988. He never saw the Large Hadron Collider confirm his predictions about running coupling constants. He never saw the precision measurements that verified his theory to 12 decimal places. He never knew how completely his ideas would dominate 21st century physics. But in his lectures and his books, Feynman left us something more valuable than predictions. He left us his way of thinking. He believed that nature was not trying to hide from us. He believed that the universe was comprehensible if only we asked the right questions. He believed that the goal of physics was not to manipulate equations, but to understand what those equations were telling us about reality. And when he hit an impossible infinity in his calculations, he did not conclude that reality was broken. He concluded that his understanding was broken. He went back to basics, asked what was actually observable, and rebuilt the theory from the ground up. That is what a great physicist does. The vacuum polarization crisis taught us something that seems almost mystical when you first hear it, but is backed by rigorous mathematics and experimental verification. Empty space is not a backdrop. It is a participant. No. Every electron in your body is swimming in a sea of virtual particles that screen its charge, shift its energy levels, and ultimately determine the strength of every force it feels. The emptiness between the atoms in your hand is as full of activity as the atoms themselves. When you look out at the night sky and see the darkness between the stars, you are not seeing nothing. You are seeing vacuum, and that vacuum is alive with quantum fluctuations, with particles flickering into existence and vanishing, with fields oscillating and interfering, with the deepest structure of reality playing out on scales too small to see but too important to ignore. Feynman called physics the most beautiful of all the sciences because it revealed the hidden machinery of the universe. Vacuum polarization is part of that machinery. It is hidden from our everyday senses, but essential to our everyday existence. So what should you take away from all of this? First, that crisis is often the doorway to deeper understanding. When Feynman's equations gave infinity, it was not a failure. It was an invitation to think harder, to question assumptions, to look for what he was missing. The infinities were not the end of the theory. They were the beginning of a better theory. Second, that the universe is stranger and more wonderful than our intuitions prepare us for. Empty space is not empty. Charges are not fixed. The properties of particles depend on how closely you look at them. Reality is not a solid thing you can hold in your hands, but a dynamic, buzzing, flickering process that only makes sense when you understand the relationships between things. Third, that honest confusion is the starting point of real knowledge. Feynman never pretended to fully understand renormalization. Yes, he used it because it worked, not because it satisfied him philosophically. He was always looking for a deeper answer. That intellectual honesty, that willingness to say, I do not understand this, even while using it brilliantly, is what made him great. There's a quote from Feynman that I think captures his approach to physics better than anything else he ever said. I would rather have questions that cannot be answered than answers that cannot be questioned. The vacuum polarization crisis gave physicists questions they could not answer. What is the bare charge of an electron? What is really happening at infinitely small distances? Why do the infinities appear at all? Some of those questions have been answered. Some remain open. Some may never be answered. But the asking, Feynman would tell you, is the whole point. Science is not a collection of facts to be memorized. It is a process of inquiry, of honest confrontation with nature, of admitting when you are wrong and pushing forward anyway. The instant Feynman knew his theory was wrong was not a defeat. It was the moment everything became interesting. Well, The quantum vacuum surrounds you right now. As you finish reading this, it permeates every atom of your body. It determines the forces that hold you together. And it is fluctuating constantly, invisibly, essentially. You are made of charged particles swimming in a sea of virtual particles, all participating in a dance that has been going on since the first moments of the universe and will continue until the last star goes dark. If that does not fill you with wonder, nothing will.